A collapsed enterprise IT implementation evaporates millions in capital, completely freezes hospital operations, and immediately stalls patient care. To prevent these outcomes, organizations rely on system selection. This phase covers the entire lifecycle, from the moment a vendor sunsets an old legacy system to the final signature on a new contract. Most catastrophic failures stem from internal missteps, like poor change management, prematurely ordering physical hardware, or proceeding with undefined project scope. The sheer scale of deploying an electronic health record or a computerized provider order entry system means a single planning gap ripples across every clinical department in the hospital. A successful go-live depends on the rigorous application of a structured methodology to manage the transition. That methodology is the System Development Lifecycle, or SDLC. This diagram shows the complete SDLC process, a cyclical model used to govern an information system from its initial conception through to maintenance. But the foundation of a successful rollout rests on the first three stages: project planning, system analysis, and system design. Moving through these phases shows how a hospital's abstract business goals are systematically translated into concrete technical realities. Without this structured SDLC framework, an organization cannot align a new system with its specific clinical and operational requirements. Before evaluating a single line of software, the institution must perform information system strategic planning. This ensures the proposed technology directly supports broader business objectives, like improving the overall quality of patient care. To execute strategy, a formal governance structure is established. At the top is the Information Systems Project Steering Committee, led by the CIO, CMIO, and CAO. Reporting to them is the execution layer, the project manager leading the project team, and a user task force. Once the team is built, they conduct a feasibility study. This serves as the operational and financial gateway, determining if the organization is actually ready and resourced for the proposed change. The study weighs expected costs against expected returns. This includes easily quantifiable tangible benefits, like eliminating paper chart storage costs, as well as intangible benefits, such as improved quality of care. Establishing this clear chain of command and documenting the financial justification enforces strategic alignment and secures organizational buy-in. A major threat to any rollout is scope creep. This happens when new requirements, like deciding to add outpatient surgery features to an inpatient EHR rollout, are added after work has already begun, draining allocated money and staff. Project managers rely on specialized tracking tools to contain that scope and prevent timeline slippage prior to the delivery date. This is a Gantt chart. It records specific tasks, assigns responsible personnel, and logs linear start and end dates. It easily shows if a single task is behind schedule, but fails to visualize how a delay in one isolated step cascades to affect downstream activities. This is where a PERT chart becomes necessary. It evaluates structural interdependencies and the exact activity sequence required. By connecting predecessor and successor tasks with directional arrows, the PERT chart reveals the true engineering mechanics of the rollout. This allows the team to map out the critical path. The critical path is the specific, continuous sequence of tasks that dictates the absolute longest amount of time required to complete the entire project. Identifying these structural dependencies is the mathematical reality behind predicting and protecting a launch date. With the timeline secured, the project shifts into the systems analysis phase. Here, the organization collects data to determine its precise storage, reporting, and functionality needs. To gather this data, the team deploys closed-ended questionnaires for rapid, broad, quantitative feedback, while utilizing semi-structured interviews for deep qualitative insights from individual users. They also rely on direct observation. Watching end users perform their jobs is required to validate actual clinical workflows, which often differ from assumed administrative policies. This flowchart illustrates how those validated workflows are mapped out. By visualizing standardized steps, like a coder selecting and reviewing a health record, the project team identifies bottlenecks. Tracing these logic paths reveals exactly what the architecture of the new software must be capable of executing. Thorough systems analysis translates complex human clinical realities into objective, codifiable functional requirements. Those completed functional requirements dictate the final decisions made in the system design phase. First, the organization determines its hosting strategy. They can either pay for scalable, remote cloud computing services or invest in an in-house server infrastructure and custom prototypes. Second, they must decide on the software architecture itself, choosing between an integrated system and an interfaced system. An integrated approach, often called best of fit, utilizes separate applications designed to work together on a single shared database. Conversely, an interfaced approach, or best of breed, connects a patchwork of highly specialized independent products linked via data translation bridges. These foundational architectural choices dictate the organization's long-term operational efficiency, maintenance costs, and vendor lock-in risks. Ultimately, the system development lifecycle forces a healthcare organization to critically evaluate its own business practices before it evaluates a single software vendor. A project protected by Gantt timelines, PERT dependencies, and rigorous flowcharting proceeds methodically from sunset to go-live. By the time an organization reaches the vendor contract phase, the SDLC ensures they are procuring a strategically validated tool rather than an unvetted IT upgrade.